Okay, this example is applied to the issue of getting the force between two wires, parallel wires. So here you have two infinite wires along the x direction, parallel to the x-axis, and the two wires have the same current, and the current is going in the minus x direction in this case, and it's the same value current, and the distance between the two infinite wires is a. And then on this triangle that has the same sides, A and A and A, you put on the z-axis a wire at this location, a distance A from this wire and a distance A from this wire on the z-axis, and the current going in this portion of the wire is I1, pointing in the positive I direction, and the wire has a length L. This portion of wire has a length L. And we want this portion of wire to levitate. We want to see what is the condition on the currents such that with the current I1 is given to be 100 amperes. What the question is, what's the current I, which is the same as the current here? These two currents, they have the same value. What's that value of current that will make this piece of wire levitate? Levitate means it just stays there in space. It doesn't fall down or goes up. It just stays put in that location, suspended in space. They gave you A, they gave you L, they gave you the mass of this part of the wire, and they gave you the current I1. So if we look at this problem looking in the minus x direction, what would you see? You see the infinite wire here with the current going into the page, the infinite wire here with the current going into the page, the finite piece of wire on the top here on the z-axis with the current coming out of the page with the value I1, and here the current is I and here the current is I. This we'll call it the left wire, this will call it the right wire, and this will call it the finite wire. So what's the direction of the force on this wire, wire number 1, due to the left wire? First, since the current here is opposite the current here, then the force will be repulsive. We showed that before in the theory part. So the force will be pointing away from this wire, repulsing away from it like that. And what will the direction of the force be on wire, this finite wire, due to the right wire? Again, the two currents are opposite to each other, so the force will be repulsive, so it will also repel the wire to be this direction. Then, what would the equation of motion then be for this wire? It's fixed in space, it's not moving. What would the equation be? Apply Newton's law to this wire with zero acceleration. It's just fixed there in equilibrium. So these are the two forces that are acting on it in the vertical direction upwards, and the value of each one of these forces is mu naught I1I times the length of the wire over 2 pi a, where a is the distance between the two wires. So this is what the magnitude of one of these is. So what are all the forces acting on this finite wire? There are these forces, the two F forces due to the other wires, and there's also gravity. So this is basically what the two forces acting on the finite wire are. The gravity is mg, pointing downwards, and then if you take this F and you get the component of the force in the vertical direction, which is F cosine theta, but you have two of them, so you get 2F cosine theta, and that's what the force is acting vertically upwards. So in equilibrium, when those two forces are equal, then you'll get equilibrium, and then this finite wire will just stay suspended in space. And so then we should equate the 2F cosine theta to the mg, and you get this equal to that. And then from here, the only unknown here is the current I. Everything else is given. And so you can derive what the current value is. It turns out to be 113 amperes.